Good afternoon, world. This is S. Gold, back with another open source software video. Today I'll walk you through the new DacWizard application. The purpose of DacWizard is to configure DynamicAnimControl for an animated model. Formerly, in order to configure a control, you had to write Java source code by hand. The new application is called a wizard because it has a graphical user interface structured as a linear sequence of steps to guide you through the process. The process still involves human creativity and judgment, but the learning curve is hopefully much less steep now. Step 1. Locating the model's J3O file in the file system. Start by clicking on the button labeled Browse the File System. Then navigate until you reach the file you're looking for. It has to be a J3O file. So I've selected Puppet. Now click Next to go to the step 2, which is loading the model. For a model composed of multiple files, it might be important to set the asset root correctly. The wizard uses heuristics to guess where the asset root is, but if it's wrong, you can correct it using these plus buttons. Then click on the Load and Preview button and study the preview to ensure you loaded the correct model. You can use the WASD keys to view the loaded model from different angles. And then you click Next to go to step 3, which is selecting skeleton bones to be linked. Here there's a multi-select box containing all 91 bones in Puppet skeleton. Initially, no bones are selected. In order to proceed, you must select at least one bone. Selecting a bone causes its description to be highlighted in yellow. Good rule of thumb is to just select the most important bones. We're going to skip over bones that don't directly influence the mesh, like the root. We're also going to skip over some minor bones, like the fingers. Probably don't want to simulate the skeleton in that level of detail. Also going to skip over these IK bones, which don't influence any mesh vertices at all. So we're going to do the arms and the legs, the hands and the feet, but not the fingers, not these control bones. That's it. So I've selected 26 bones. But it's telling me there are no mesh vertices for the torso. Now you have to leave some mesh vertices that aren't influenced by any linked bone. Those leftover vertices will determine the shape and location of the torso, which is the root of the ragdoll hierarchy. In the case of Puppet, we'll deselect the hips bone to provide some mesh vertices for the torso. Next, the application studies all the canned animations in the model and collects a random sample of skeleton poses. It uses this sample to estimate what the range of motion should be for each joint in the ragdoll. The estimation process lasts for 10 seconds. Not the most elegant solution, however, random sampling was relatively easy to implement and works fine. The algorithm assumes that the canned animations cover the full range of motion for each joint. If they don't, you can always adjust the ranges later. And step 4. Step 4 is configuring each physics link. There's a select box containing all the links, one for the torso and one for each linked bone. And like the bones, the links are arranged in a tree. Below the select box are controls to configure the selected link, including its mass, its shape, the center location, and the range of motion. Currently, the torso link is selected. That's the root of the ragdoll hierarchy, and as such, it doesn't have a range of motion. However, all the bone links do. Default shapes and centers are usually okay, so I'm going to proceed directly to step 5, which is testing and saving. Testing in this case means clicking on the Go Limp button and watching the resulting ragdoll simulation. If you know something you want to change, you can always go back, use the back button to return to step 3 or 4. For instance, It's a little hard to tell, but let me hide the meshes to make it clear. It's wasteful to link two bones in each upper arm and each lower arm. Most humans don't have a joint there. I don't know why Nathan chose to model Puppet in that way. Also, the upper arms, looking at it as a mesh again, the upper arms are essentially cylindrical. There's no need for detailed convex holes, which are relatively costly to simulate. So let's go back to bone selection and deselect the upper arm 2 and forearm 2 bones. So upper arm 2 left, forearm 2 left, upper arm 2 right, forearm 2 right. Now there's only 21 bones linked. And the vertices that used to belong to upper arm 2 will now be inherited, if you will, by upper arm 1, which is the first link above them in the skeleton tree. And after clicking the next button, the wizard goes through the estimation process again for 10 seconds. And when you look at the link hierarchy, it's going to be a little bit simpler now. For each side of the body, there's just one upper arm and one forearm. And the forearm is directly connected to the hand. While we're here, I want to take the opportunity to change the shape of the upper arm. So I select upper arm left, change the shape from vertex hull to two-sphere, which is essentially a capsule shape and should be much less costly to simulate. I do the same thing for the right, upper arm right, change the shape, click next. Now we can test the new configuration, which works fine. And if you look closely at the arms, now the upper arm and lower arm are clearly each one bone, or bone link, I should say. So you can tell there are fewer joints in the arms, and the shapes of the upper arms are now just capsules. Let's say we're satisfied with this new configuration. Next step is to click on Save Configuration. The wizard writes the configuration file and tells us where to find it. And of course, it's a Java file. Code has been automatically generated for you. That's it. In closing, note that both DynamicAnimControl and DacWizard are part of the Minier project, which is open source. The source code resides in a GitHub repository under my GitHub username, which is Stephen Gold, StephenGold. And this is S. Gold signing off.